Alrighty, so yep, Kent and I are going to talk through the blockchain structure. So that'll include sort of basics of what the blockchain looks like, as well as a little bit about Casper and proof of stake. It'll be sort of a high-level overview. So we'll start off with a quick recap of Rolang, sort of a quick summary of everything that Kyle talked about yesterday, just enough to get us through some of the code examples in here. We'll talk about how RChain is really just a giant Rolang term, which is super cool and makes everything really easy to think about. How you'll interact with the RChain state, what these blessed contracts are and what they do, and then Kent will take over from me and he'll talk about some more details of what the block structure actually looks like and Casper stuff. So in Rolang, all computation is done by passing processes over names, or channels, depending on the nomenclature you want to use. And I've given sort of a brief list of what the processes in Rolang look like. This is not an exhaustive list. It's just to get us through what we need. So there's concurrent composition, P par Q. These are two processes that are in principle running at the same time. And we have send and receive. This is the sort of basic computational piece of Rolang, where you can send a process P over channel X with the bang, and you can then receive it on the other side as a name with the for, and that spawns a continuation as well. And you can create a new unforgeable name, and that name can only be referred to in its own lexical scope, as I note down there. So names in general are just quoted processes, so the whole thing is sort of built on top of processes, and processes are things that look like this. You throw an at in front of one to quote it, so now you've got a name. Unforgeable names are just quoted unforgeable processes, but names can also be public, as in just a piece of source code that you can write down. We'll talk, the difference between unforgeable and public names will sort of come back again and again as we're talking through interacting with the blockchain. It's an important distinction. And like I said, unforgeable names can't be referenced outside of their lexical scope. And so in particular, what we're going to see that means for us is that you can't reference an unforgeable name from off of the blockchain. It's not going to happen, but we'll tell you how to make it all work. You can send an unforgeable name by packaging up and with a bang sending it across some name, right? So that is something that you can do to share unforgeable names, even though you can never write one down. Right, so that'll be important, and we'll see how that works. Contract definitions are just replicated receives, as in it's a for that sticks around forever. There is a slight difference in the payment model, which Joe will talk about in the next talk, I think. And most importantly, when a send meets a matching receive, they have a comm event that produces the continuation, and this is exactly how Rolang makes computation happen. So RChain is just one big Rolang term. Everything that exists on chain is part of that term. You can think of it as just a process, concurrent, another process, concurrent, another process. Most of them will be contract definitions, right? So you'll be able to invoke those contracts. And all a block is going to look like is it's going to tell you what the past state was, what the past Rolang term was, what the new Rolang term is, and what happened in between, what new code was added, and what comm events happened. And Kent will get into the details of what that looks like. And I do have a footnote here that namespaces should probably be thought of as their own Rolang terms, but that's a detail, and we won't worry about it too much. So RChain, one big Rolang term. And so now we want users to be able to, or app developers to be able to interact with the RChain state. So we have this notion of a deploy operation, which is just adding something into the state. So if P is some valid piece of Rolang code, you can deploy P, and you give some payment-related details, which, again, Joe will get into a little bit more detail on how your payment leads to computation. And what happens is if S is the current blockchain state, then by deploying P, the new blockchain state is S par P. And there will be some comm events that probably happen as a result of that, and those reductions will be recorded as well. So, well, we'll talk a little bit later on about the difference between wallets and purses. That came up actually a couple times in Menda's talk, like talking about what is a wallet and what does that API look like. So we'll talk a little bit about that later on. But what's important to note here is that even though I'm talking about this as if it's the standard Rolang, there will be some nuances and subtleties about the runtime environment of the blockchain versus the runtime environment of the interpreter that's available today. Basically, like the important differences are those related to the security of having multiple users being able to interact with it at once. And we'll talk a little bit more about some of those differences later on. But notably, there will be restrictions on certain public names. So the Registry Contract is going to take care of that, and we'll talk about more later. And again, I've noted at the bottom of the slide, this is a key point. Unforgeable names cannot be accessed in a deploy event from off-chain. Why? Because you can never write down an unforgeable name, right? So P has to be some valid piece of Rolang code. And you can't write down an unforgeable name outside of its lexical scope. So if its scope is on-chain, you can't write it down in your deploy. This means that you're going to need public names in order to have entry points into the unforgeable names that are useful on the blockchain. And we'll look at some examples of that later. So blessed contracts are contracts that'll be around from the Genesis block, and they're here to do system-critical tasks that just need to get done. Things like taking care of the rev mint and registering public names for use as contracts and for proof of stake. So these blessed contracts, because they're so important, they aren't owned by any user, weren't deployed by any user. They have just always been there since Genesis. No one pays for them. They will just be there for taking care of the system tasks that need to be taken care of. And so over the next couple slides, I'll go through an overview of these blessed contracts and talk about how an app developer might interact with them. So we'll start with the Rev contract. The core concept here is the idea of object capabilities and authority. So a mint has the authority to produce non-empty purses. Or equivalently, you can think of it as the mint has the authority to create new tokens. And that sort of makes sense. That's why we call it the mint, right? That's in line with how money works in the real world as well. Purses, on the other hand, only have the authority to produce empty purses. And this is an important piece of authority. We'll talk about how you might use that for your software development. And they can accept deposits from the same mint. So if I've got a purse and you've got a purse, and you hand me your purse, I can take some coins out and drop it into mine. And this is sort of the most basic version of transferring tokens from one party to another. And all of these authorities are managed through unforgeable names, right? So this is going to be very important when we're talking about how do we actually access these objects if they're only available through unforgeable names. And the answer is going to be public names that modulate that authority, right? And that's what the next bullet is, that the authority to the rev mint is going to be very important. We can't just have any old person printing off money, right? So the authority to the rev mint is going to be delegated based on some business logic that the co-op gives us, right? Maybe there will be multiple signatures or something along those lines, but there will be a security aspect there. There will probably also be something built into the proof of stake about rewarding validators with new tokens, that kind of stuff. And what's cool is there is actually code available that does all these things already. It's on GitHub. You can go look at it. The link is there. It's the makemint.ro. And it's based on the E programming language sample, where these object capabilities ideas are also talked about in more detail. And that link is given there. So let's talk about purses versus wallets. So a purse is a full-featured object reference. You can think of it as essentially a bag of coins. If I hand you a bag of coins, I can't stop you from taking the coins out. You can basically do whatever you want with a bag of coins. And so the most important piece of security for it is to make sure that no one else can get at my bag of coins. It has to be referenced through an unforgeable name so that no one else can get access to it unless I allow them to, unless I send them the unforgeable name myself. Wallets, on the other hand, are contracts that are on top of a purse. They wrap the purse in some sort of security so that you can safely access it from off-chain. Right? A wallet contract can be stored at some public name, accessed via a deploy, and it'll do some security check to make sure that only you and the people you want to can get access to it. So as a simple example, it might do a signature verification in the same kind of way that Aetherium works today. But what's cool about this is contract-wrapped purses are way more general than just personal token storage. You could use them to put up a storefront, sort of, where you've got in the back a bag of coins, but people only have deposit access. They can only give you money, they can't take it away. And so we would call this an attenuated forwarder. It's something that gives authority, but only partially. Only the authority that you want to be handed out. Or you could develop contracts that have purses behind them to do fun things like lotteries or betting, where the idea is that the participants hand the contract their purses, the contract dumps them into the pot, and a winner is chosen in some way, and that purse is then given to the winner. But most importantly, of course, proof of stake is basically just a contract wrapping a purse. The people bonding will give their bonds in a purse. It will take it, put it into the protected Casper purse, and they won't get that money back until they unbond. And we'll talk more about that later as well. So let's try to make this concrete with an example. So I'll say now that this example works with the makemint.row as it exists today. Implicitly, there's some other code in the background that's an API. And that API is sort of subject to change. And most likely, the user experience will be a lot smoother than this. There will be quite a bit less code than what I've shown here. But I want to reveal all of the moving parts, which is why I've sort of given this detailed example. So in the first line, we're just declaring a bunch of channels that we're going to use throughout the code. Nothing super interesting there. And on the second line, we are calling the wallet contract, right? It lives at this public name, and so we can call it in our deployment directly. The nonsense sig there in italics are just placeholders, right? Imagine that there's actual values in there. That would be valid. And so what this contract is going to do for us is check that the nonsense signature line up with what it thinks it should be and return us back a result on this wallet channel. And we're doing a match expression on that result to see what we got back. And we're either getting back a purse, in which case we're going to do stuff with that purse, or we get back some error and we want to report that error back to the client, right? This the purse shouldn't be given out because they failed to pass the security check. So what do we do in the case that we get the purse? Well, we want to make use of that authority to create empty purses through something called the sprout operation. So what we're doing is we're creating a new empty purse and storing it on the channel called Bob payment channel. And then we use the for expression to pull out that purse. And now we want to deposit on the second line 10 tokens from the purse, our main purse, into the payment for Bob. And the reason we're doing this, again, remember, is that you want to protect your own purse, right? You don't want to just give the reference directly to Bob and say, please only take out 10 tokens, no more, right? You don't want to trust them to do that. So you make a separate purse to put those 10 tokens into. And that's what happens on the second line. It has a success channel, which just returns a Boolean, and we make sure that the transfer to the Bob payment was successful, and then we just send Bob the purse on his own public channel with a little note from Alice saying, here's my 10 rev. Or it could have been the case that maybe Alice only had 9 tokens in her purse, and so the deposit might have failed, in which case we have to report that error back to the user. So again, the idea is about delegating authority only as far as it needs to be delegated, right? Bob only needs to get 10 tokens, so we only give him 10 tokens, and we only give him the purse that contains those 10 tokens. I should also mention that on the other side, Bob should probably immediately take those tokens out and put them in his own purse, right? Because we could imagine that maybe Alice actually sends this purse to Bob and Charlie, and as trying to do a sneaky double spend type thing, and to prevent that from happening, you would want to take the tokens out immediately. Or even worse, maybe Alice just takes the tokens out after sending the purse to Bob, and Bob gets an empty purse, and Alice goes, "Oh no, there was 10 tokens in there, I swear." Right? And so it's important that when you receive a purse from someone else, you take the tokens out and put them in your own purse that you control, right? You want to make sure that you have guarantees about what's going to happen to your tokens because you control the reference that has all of the capabilities for those tokens. You control the purse reference. Maybe I'll pause there for a minute. People are giving me confused glances. So let's get some questions.
Where's the storage actually getting updated of the balances or the?
So that happens in the purse itself. So if you look at makemint.row, that GitHub link there, the purse has a bunch of code that handles the balance change. So if you look at line 2 on this slide, this deposit method is taking 10 tokens from purse, the second argument in the list, and dropping it into Bob payment. And the conservation of tokens there is handled in that method call. And because the purses come from the Rev blessed contract, it's guaranteed to work. You can see that this code is correct, and you can't forge it because you can't forge the Rev unforgeable name. Yeah, so you could use any mint. You can, if you wanted to make a token of value that was not the official Rev, then you could also use the same makemint.row, and it would have all the same capabilities that Rev has. Notably, the reason that we do things this way is because it scales, right? It's distributed. There's no single ledger of balances that you have to update. And that's not very scalable to do it that way, right? If I have to say, okay, everyone stop, no one touch the Rev balance sheet except me, I'm going to update this balance. Okay, now everyone can do their thing, right? Having a global state that you have to get a lock on every time you have to do a transaction is inherently not scalable. This distributes everything so that just by design, the contract doesn't let you create new tokens, and you don't have to worry about keeping track of the global quantity because you know the only way to make more tokens is from the mint, and the mint authority is protected. Yeah, everyone on board with this? All right.
I'm sorry. I'm very, very new to rolling, so I'm having a little trouble following this. Purse is your own purse, right?
Yep.
And then the Bob payment channel is.
It's just a new channel that we declared back here. It's just some channel.
Over which, what's coming in on this is you get
the empty purse. You're getting back a new empty purse on that channel with the sprout method call. And again, don't get too bogged down in the details. I encourage you to go look at the contract and check out the code and sort of play with it yourself. But in practice, right, we'll have all this behind some very convenient API call where you can just say, here's my wallet, here's my security information, send 10 here, right? And in the background, all of this will happen. But just to reveal some of the moving parts and try to help you understand what's going on, I thought it'd be nice to sort of see the example fleshed out in a little bit more detail than that.
Here at client, we're sending messages back to, say, the wallet UI or something like this?
Yeah, so at client, don't think about that one too literally either. At client is meant to represent a channel that comes back to the user, right? It's the status report, if you will. How exactly that works will be different than this, but this is modeled after the current standard out implementation that we've got, where you just say at standard out to print a standard out. This is at client is in, send something back to the client letting them know. But we'll refine this and make it a little bit more clear when we actually roll it out for the blockchain.
And so then, what is stored at the Bob deposit hash name?
It is a contract that's listening for other purses, and when it receives those purses, it'll dump the coins into Bob's main purse.
Cool, thanks. And then you could like update your main purse or something.
Oh yeah, totally. Yeah. Okay, so let's.
One more question.
Yep.
Why there is a distinction between purse and wallet? Eventually, you are, creating a wrapper around purse and telling it a wallet. So why do we really need that distinction?
So purses are conceptually different from wallets, right? Purses have all the object capabilities that you could ever want to possibly do with money, right? Purses are a modular and distributed way of handling money that doesn't concern itself with security issues. We delegate that somewhere else. In fact, we delegate it to the wallet, right? So this is about having a scalable transaction system that separates concerns in the way we want them to be separated. So the wallet worries about security, the purse worries about moving around money and maintaining the conservation of rev balances.
It's super modular. So like the multi-sig wallet will be 3 lines different than the single sig wallet because they both just wrap a purse and do a security check. And you can know that the purse part is correct. You don't have to worry about a bug in that part of your code. That's one of the advantages of using a reusable component.
The way I see that,
Well, also, just to be clear, in typical parlance on the blockchain, a wallet is a client-side thing that stores information that lets you interact with balances on the blockchain. Because of the way RChain is structured, there's the purse, which is usually listening at an unforgeable name and is therefore not accessible from off the blockchain. There's a wrapper around that we have been calling wallet, but is the part that is necessary to expose something to the client wallet so that it can interact with the code on the blockchain. So there's this extra layer that's containing the purse that in this presentation has been calling a wallet, but it's not the client-side thing. So just to clarify that.
Yeah, you might think of it as being more akin to an Ethereum account, but except it's more general than that because you can have different security than the typical Ethereum account does.
So the way you're describing, I see purse is kind of virtual thing, and nobody's going to interact with purse essentially. That's what you mean?
It will probably be a rare circumstance, especially for an average user, to touch a purse. DApp developers might want to work with purses directly from time to time, but the point is, you ask yourself the question, do I want to move around money? If yes, write some code that interacts with purses.
So the way I see Ethereum has one of the biggest problems they have is the account, right? So they have different definitions for account and the contract, right? If we are following the same way, if you are not, then I see Mike is nodding on that one. Then I don't think anybody can interact apart from contracts with the purse. That's how I'm seeing that. Is that correct?
You can purses will basically live at unforgeable names, and so the only way to interact with them will be via code.
It makes sense. Thank you.
So I just want to make a statement that I hope means I'm understanding what you're saying. In Rolang or RChain, you don't ever send people tokens. You send them purses.
That's the model we're going with, yeah.
Okay.
And tokens are contained in purses.
Got it.
All right, cool. So let's...
Follow-up question on this. I think now you gave me another one. So suppose if I have 10 tokens and I have a purse ABC, I'm sending these 10 tokens, whatever the token, to Kaya, then what will happen? The whole purse will transfer to his wallet, or
so
I'm kind of confused with the mechanism.
Like in the example I just showed, if you want to send payment, you create a purse specifically for that payment, dump in the correct number of tokens, and send that purse over.
Yeah, and then I'll empty it.
Oh, so okay, now great. So now the space comes into picture. So what will happen? So the purse I had, where it's going to reside? I would understand that it's going to stay in the R space. Then what will happen to that continuation in the memory in R space?
I'm not sure I understand your question.
Yeah, I don't,
First, I understand what Mike was describing yesterday. First is a sort of continuation in our space. It's going to reside that way.
So
And then
just
it's
to be
going-
clear, in Ethereum, you run one contract, and that has a data structure inside that contract with all of the balances in it. In RChain, it's a much more distributed thing. You have thousands or hundreds of thousands of purses, each one containing some small number of tokens of a particular currency. The code of those purses allows them to exchange that securely. So there's no central place for collection, an audit of all of the balances. You would have to look over the entire blockchain to see what the balances were on all of these things. So if I give you a purse object and I let it go out of scope and you let it go out of scope, it's gone. It gets garbage collected. So you can get deflation by burning things. You don't send it to a particular address. You just let that purse containing that much money go out of scope and it disappears.
Sorry to just sort of jump in late, but that sounds a lot like a UTX model with garbage collection on your dust, for example, right? Whereas you don't get garbage collection on dust now, and it's a huge problem in Bitcoin. It sounds like these purses sound much more like UTXOs than like the Ethereum account model.
It's not really like UTXOs. So, for instance, you can absorb the contents of one purse into another and just have a larger purse. So the reason that you shouldn't think of passing around tokens is that the tokens are just basically integers. And so the purse wraps up the integers with the correct security code to say, oh, well, somebody can't just pass me an integer, like, with enough information to trust the integer.
all right, cool. So we'll try to run through the remainder of this a little bit quickly, since we took quite a bit of time with that, but it was a good discussion. So the basic idea behind the registry contract is that we need public names for accessing the blockchain, right? Because you can't access unforgeable names in a deploy. But we don't want it to be the Wild West of public names, because you could get, phishing. Someone writes a misleading-looking public name, and you might trust it based on the name, but in fact you don't know who's on the other side. Or you might have someone trying to intercept messages for your contract, right? You make some great, super useful contract, and then someone else decides, oh, I'm going to make one with the exact same name and set of arguments, and start intercepting messages that were meant for your contract, and just do some other nefarious thing with it. And so you want at least some regulation on public names so that you get this kind of security guarantee. And so the blockchain runtime is going to prevent sending and receiving on these special names, which are generated with backticks, which we call URI processes, and they start with row:. And so you put an @ in front to make it a name. And so the registry lets you create a contract at one such name. So this is an inexhaustive list of different sorts of names you might support. So say you want to put a contract at some public name, and you want to reference it by its code hash. That's a supported behavior, where you just say row: hash, algorithm for your hash, and then the actual hex representation of it. Or similarly for public keys, for identity purposes, row: public key, : algorithm for key generation, and the actual key afterwards. And both of these, you need to submit evidence that you actually own these things, right? So when you ask to have a particular hash, you have to submit the code that hashes to that hash. And when you ask to control a public key, you have to show that you own the private key by doing a signature type thing. And we'll also have some system for domain names and registering of those domain names. And I'm just going to skim over this because it's not super important. But the basic idea here is that when you ask the registry contract to register a name, what it gives you back is actually an unforgeable name that has the authority to write something to the tuple space that actually allows that contract to appear there. And the runtime will automatically strip out the unforgeable part so that it's just stored at the original public name. And then other people will be able to call it after that. Sure.
So looks like to me all the contacts will be available in the public domain sort of thing, right? So do you have any idea, or are you guys thinking about zero knowledge proof, how we can hide if I don't want to allow my contact to be seen outside, in public domain? Or how do we create a private registry of the contract?
Well, if you want a contract to not be accessible, make it at an unforgeable name, right? Just don't make it at a, the only reason you want to make something at a public name is so that it can be publicly accessible, including by yourself in future deployments, right? So what you could do is write, say you've got a suite of unforgeable names that have contracts at them, and you could front that with one public name that allows you to maybe meet some security challenge before you get access to the contracts you want.
So is it going to impact any storage if I have a private contract, I don't public it in registry, then?
It's all the same on the back end. It's all in the tuple space.
Great, thanks.
Kyle's got another comment.
So if you have a contract at a private name, and we can prove that no one else would ever be able to write to that, or unforgeable name rather, if we can prove that you can never write to it, we'll just garbage collect it, because it will never have any effects.
All right. So now we'll talk real quick about the proof of stake contract, then we'll let Kent come up here. So the proof of stake contract handles bonding, unbonding, slashing, and rewards. This is key to the Casper protocol because that's where the weights come from. But Casper itself sort of runs at a layer below Rolang, at least in the first implementation. We'll write contracts for it at some point in the future. Unbonding is what gives us validator rotation, and slashing is what basically makes it costly for people to do bad things. We've got a pretty detailed write-up on the wiki that people can read if they would like to, but I'll give a quick overview here. I'll also just mention as a caveat to cover my own ass that this is all subject to change, and will probably change at least a little bit in the future. But the general scheme of it is that every region has certain properties related to its proof of stake set about it. Things like how many active validators you can have, how many validators can I have waiting to become active, how many validators can leave over a given time span, right? You want to prevent horrible things like all the validators dropping off at once. Also, how long does it take before I actually get my original bond back? We'll talk about that in a little bit more detail in a minute. As well as max and min bond amounts and some cryptographic requirements around what you actually need to be able to do to be a validator. And that's kind of hazy right now as well, what specifically those are. But the broad strokes of bonding are you provide some form of identification and a purse that contains the tokens for your bond, as well as the evidence that is required of you. And the bond is successful if your evidence checks out and you give a number of tokens in between the max and the min. And the validator becomes active if there's an open spot, but if you've already hit your maximum, you become queued. But notably, you are still bonded, so your tokens are held even though you're not yet actively validating. For unbonding, you call the proof of stake contract saying, please unbond me, here's my signature so that you know it's me, and a return channel. The return channel is where you will get your money back eventually, but not right away. And the reason you don't get it back right away is because you could have an attack in which you start rewriting history sort of behind where you unbonded, and because you wouldn't have any active bond right now, no one can slash you for that. To prevent that kind of thing from happening, we have a holding time, which is yet unspecified as to how long that is. So an unbonded validator is inactive. They are not actively doing any more validation work, but their tokens are still held, and they can still be slashed until after the holding time is passed. And when they unbond, if there's someone in the queue, randomly one is chosen and they become active. So slashing, the offending validator loses a portion of, possibly their whole stake, depending on the offense. All slashing requires cryptographically verifiable evidence of the offense. And any validator can slash any other validator. Basically, the broad strokes of how this will work is the accuser sends a message to the proof of stake contract saying, this person did this bad thing, here's the proof of it. It goes through if the evidence is verified. And slashable offenses include equivocation, as per Lad's talk yesterday, creating an invalid block, and possibly something related to performance, but that's, again, still kind of up in the air. And finally, getting rewarded. The X validator is allowed to get paid for their rewards by asking the proof of stake contract to pay it out to them on a return channel where a purse will be sent. That's it for me, and maybe I'll pause for a quick minute if anyone has questions about any of that proof of stake stuff, and if not, we'll pass it over to Kent. All right.
So here's a diagram, and as you can see, there are a number of components to RChain's block. We'll start with the body, and so the body has a post state, and currently this is just an implementation ease. Essentially, in the future, we plan to remove this and just have the post state hash, as you see in the header. There will be a new code. Essentially, this is the deployments that will occur in that block. And so if you're familiar with Aetherium, this is very similar to the transaction try that they have. Similarly, we will have a receipt or a reduction log. And this will be an execution DAG that represents a partial order of how things were executed or how the reductions were done in the block. And the point of this is that you can, following this reduction log, you can get the post state that you put in this block. And so, again, if you're familiar with Aetherium, this is similar to the receipts try. And if you look over to the header, you'll see that each of these components have a hash that will be stored. The one thing that I haven't mentioned yet is the ordered list of parents. So the hash of which will be stored in the header. This is essentially, a lot of you might be familiar with having a single parent. And the idea here is that, as you'll see later when I describe more about specifics of Casper, this will allow for an optimization that will allow us to have a higher transaction throughput. And so all those elements in the header will be hashed, and that will turn into the block hash. And that will be another component in this block. So at the bottom, you see two more elements, one of which is the signature, which you can derive the creator of the block. And you see the justifications, and these are the pointers to the latest blocks for all the validators. And so with that in mind, I would like to move on to specifically how Casper will be implemented for RChain. And so a lot of what I'm about to say is already outlined in Vlad's paper, and also it's been implemented once by Nate over here with the CPC Casper repo. And so I guess one thing I want to sort of, or one way I want to frame this is I want to sort of separate Casper into three components, one of which actually Mike already has touched on, which is about how equivocations and slashing works. But the second aspect is, how do you figure out which block to build on top of? What is the latest tip? And this will be done in RChain through inclusive ghost. I'll describe this later. But the third aspect is finality. And this is important because, well, sure, you can figure out what is your latest tip and where you want to build a block, but you also want to know for the purposes of double spend or essentially to prevent that, you want to know which blocks will remain in the history no matter what or how the protocol proceeds. And so first up, I just want to explain this diagram here because we'll be going through a lot of examples with it. And so first of all, the perspective of this diagram is such that we're viewing it sort of from an attacker's view, so to speak. And another way I like to view it is as from the perspective of a validator that has almost 0 weight and is looking at this. And so if we zoom in to this, you see a bunch of ovals which represent blocks. And on the x-axis, so to speak, is the columns which represent validators. And then the y-axis represents the time. And so I've sort of conveniently drawn out these diagrams such that every block is in a different time step. And in reality, some of these blocks will be produced in parallel. But just going into the actual DAG that's going on, you see 2 types of arrows. One of which is the solid arrows, which represent the parent, and the dotted arrows represent the justifications. And so if we look at the topmost block in the left validators column, we can see that there's a chain formed from it, where you can go down, down right, and then down left, and that's one chain. And then for the right validators, starting from the top block, you have going down, and then down left. That's another chain. And another aspect is we also have orphaned blocks. So there's 2 orphan blocks in this diagram, both of which are on the left validators column. The 3rd from the top, and then the 4th from the top. And I call them orphaned because the left validator has chosen to build on top of a new chain. And so, hopefully that explanation of the diagram is clear. And then, so I would like to move on to explaining what inclusive ghost actually is. And so first, the idea is, well, we want to figure out which block to build on. And so intuitively, like, you probably want to choose either the top of the left validator or the top of the right. But we want to see, like, actually which one it is. And so to do this, we go through this scoring process where we score every block with the value 0 first, and then we go down from the top or the latest block in each validator and then add their weight to the chain that that follows from it. And so, here I've shown the first 2 steps for each of the validators. I'm assuming this happens in parallel, but another way to view it is you could run through and add 2 for the left validator first, and then run through again for the right validator and add 3 to everything. And so when we do this, we end up with this sort of scored DAG. And as you can see, in the areas that both validators have added weight, you see the number 5 because the 2 plus 3 is 5, and that is the weight that is added. And so once you have gone through and scored the DAG, you can actually now pick the highest scored choices as you go up. And the idea here is that, well, first you start from your latest finalized block, and then you pick the choice that has the higher score. So your first choice is between 0 and 5, and then you choose 5. And then again, you have a choice between 0 and 5, and then you choose 5. And then your next choice is between 2 and 3, right? And you choose 3. And so then you're at the tip, and that red bold arrow that you see is what is termed the fork choice. And so this is the path that leads to the latest block, and you want to build, if you were a validator, on top of this block that is labeled, or the topmost block on the right validators column. And so once you've built up this fork choice, now, as I said before, you want to figure out whether some blocks on it are safe. And so to do this, you again start from the latest finalized block. In this case, it's the Genesis. And then you go up along the fork choice, and at each step, you run the safety oracle saying, asking, is this block safe? And if the safety oracle does say it's safe, then you move on to the next candidate. And then you keep going until the safety oracle says, well, we can't say whether this is safe or not yet. And then at that point, you have to wait for more blocks to be included into your view. And so the specific safety oracle that we're investigating into now is the clique oracle. So in order to describe this, I have to define what a clique is. And so a clique is a subset of vertices in the graph, in any graph, that is fully connected. And so I guess a more formal way of saying it is the subset of vertices that you're looking at form an induced subgraph that is complete. And so just as an example, here's a graph. It has 23 vertices and 42 edges. And so that automatically means that you have 23 one-vertex cliques and 42 two-vertex cliques. But what we're really interested in is the maximum cliques. And so the maximum cliques are the ones that are in dark blue here. And they both have 4 vertices each. And so they're maximum because there's no complete subgraph with 5 vertices in this graph. And so going back to the step before we ran the safety oracle on the candidate, we want to sort of build this agreement graph, which I'll just describe in more detail now. But the idea here is that you draw out all your validators as vertices. And so the one on the right is sort of represented as a bigger dot because it was the validator with weight 3, which had more weight than the validator with weight 2. And the idea is that you want to draw an edge between them if they are in agreement with respect to a candidate. And I'll describe that in more detail later. But the idea is if there's an edge or a clique in this agreement graph that you draw, then there's no way for messages within the clique to change the fact that a candidate is finalized or not. And so it's still possible that from the outside, the decision can be changed. But the important part is from within, you won't be able to change the decision on whether the candidate is finalized or not. And so if we look at the maximum clique in the graph, and we see that it's more than 50% of the weight, that means that nothing from the outside is powerful enough to change the decisions within, because we're looking at the maximum clique. And the only exception to that is if we allow equivocations. And if there are equivocations, then that means that there are messages that could change the decision that is made. And so this is where the notion of fault tolerance comes in. Essentially, the safest thing you can have is a maximum clique which involves all the vertices, in which case your fault tolerance is 1, or essentially everyone would have to equivocate in order for you to make a bad decision about whether you're finalizing a block or not. And so I've sort of glossed over the why you're allowed to draw an edge between two nodes, and I'm going to explain that now. And so this is a really simple example in the sense that you only have 2 validators, so there's only one edge in question, but there are essentially 4 properties that you need to fulfill before you draw the edge, and 2 of them are, or they're dual to each other. And so the first one is that the first validator, let's call the left one, it needs to see that the right validator agrees with the candidate. And I've represented this here as, or the specific way you do this is you start from the latest block in the left validator's column, and then you traverse down its justification pointer. And so that is the latest block that it sees in the right validator's column. And from there, you see whether the candidate is in the history of that block. And in this case, it is, because it's directly pointing below that. And so we can repeat this process in reverse, so to speak, where the right validator looks at the left validator's latest block from its perspective, right? And then it sees whether the candidate is in the history of that block. And again, it is. And so those are the first 2 dual properties. But if you notice, that's not actually enough for there to be a clique, or for the 2 validators to sort of lock in their decisions. And so the thing that you need to look at also is the blocks that follow from the latest block that the other validator can see. And so, if you've been looking closely, you might think that this is just copy-pasted from the other slide, but it actually works out well, because the latest block that the left validator sees in the right validator is the grayed out number 2 block. And so we want to look at all the blocks above that. And we want to check if all those lead back to the candidate. And in this case, it does. And if we look at the reverse, we want to look at all the blocks above number 2 in the left column. And again, these blocks also lead back to the candidate. And so that means that we're allowed to draw an edge between the 2 vertices that represent both validators. And so now that means that we have a clique with 100% of the weight. So even if your fault tolerance is 1, we can say that that candidate block is finalized. And so then we move on, as I described before, to the next candidate, and we repeat this process. And so we go through, the checks again. So this is the first check, and this time the latest block is the latest block for, in terms of the left validator looking at the right validator, is the candidate block. So that's indeed an agreement. But if you look at the other way, this time when the right validator looks at the left validator's latest block and it sort of goes down its chain, it does not see the candidate. And so this means that the right validator isn't able to see that the left validator is agreeing with the candidate. And so here, we're not allowed to draw that edge between them. And so here, that means that the largest clique that we have is just 60% of the total weight, the largest validator's weight, right? And so if that's an acceptable fault tolerance level for you, then you can say that block is finalized. But if you're being a bit more cautious about things, then you can't say that that block is finalized. And so you stop there and you wait for new blocks to come in. And so finally, I just want to go over how multiple parents will affect this. And so the largest change is in the ghost traversal, where effectively before, or it stays the same in the sense that you don't add score to the blocks that are not your main parent, which we call the step parents. But the optimization, or sort of a rule that we've included, is that if you have a block that includes a step parent, you include the weight of the creator of that step parent into your block. Except if that creator of the step parent creates a new block that conflicts, then you no longer implicitly include their weight. And so this is just a way so that we can sort of incentivize merging of blocks. And one important point to note when we merge blocks is that we can only merge blocks that don't conflict as of now. And so we don't actually use the full sort of property of the ordered list because, as it stands right now, it wouldn't matter if it was only just the main parent and then everything else. But later on, we can have sort of tighter merge disciplines based on the ordering of the parents. And so that is it for the Casper. And so, yep, that is it for the talk.
How you arrive for any particular block at consensus or finality.
Yep.
How does somebody from the outside world ask a question about finality on a block? So imagine I'm building a wallet and I submit my payment. How do I know where to ask or what to ask to get the decision of finality so I can be sure that the payment has been made?
I see. So all the examples I was giving here were from an outside perspective. So, this, when I said this first block, or this candidate down here is finalized, I meant from an outside viewer with, let's say, a fault tolerance of like 0.8, because, I said that later on that this number 2 block isn't finalized based on that outside perspective.
So for like proof of work blockchains, like Bitcoin or whatever, they're sort of arrived at consensus to wait 6 blocks for confirmation. Will there be the same for RChain? Like we should look for 80%, or what are there going to be guidelines for arriving at finality for that?
So I guess the classic threshold that you choose might be like 1/3, but I think we would need to run some simulators before we decide what the optimal fault tolerance level is. And the other important part is that you sort of want to, if possible, keep your fault tolerance levels secret, because this will make it harder for an adversary looking at the outside to try to rearrange messages such that to like stall the protocol.
So Kent has also been talking about rather general Casper protocol. In the specifics of RChain, we will either have it part of the protocol or have something running beside it that marks particular blocks as having been finalized. So it will be very clear which ones can never be changed again.
Thank you.
Great presentation, thanks. What is the validator weight? Does that just come from the size of the stake?
Yeah, so we haven't actually decided whether we want to sort of enforce a maximum or, yeah, but the general idea is that you want your stake to be, or sorry, your weight to be somewhat correlated with your stake. Yeah.
So it seems right now that the block structure and the general architecture of this doesn't really fully realize the concurrent structure that is inherent to Rolang. And like you could foresee, for example, transactions or updates being deployed in parallel and they don't affect each other. So you could have two different updates and it doesn't matter. The ordering doesn't matter essentially.
Oh yeah. So when I said earlier about how the reduction/receipts log is an execution DAG, I meant that it only specifies partial order. So when you go and verify the reductions in a block, you can do some applications in parallel.
Right, but now you still have a total ordering in terms of the blocks. So is that something that will necessarily require behavioral types to have?
You don't have total ordering on the blocks because you can have a block whose justification contains the two that you saw. So say in one block, Alice pays Bob, and another block, Carol pays Dave. Then in a third block, could take both of those as justifications and include both of those updates in what it claims the next state is. And so they're independent not only within the blocks, that those can appear in any order, but between blocks you can also do merges of state.
Yeah, the multiple parents is what enables that, right? That's one of the main, like we talked about it briefly at the end, but the typical, so like if you notice the second block there has two parent pointers, that wouldn't be allowed normally in block chains, but now we're doing a DAG. Multiple parents is how you merge state.
Also, you mentioned the full concurrency of Rolang. Because on the blockchain we can see when messages have been delivered, we could use a synchronous calculus. That is, we could have continuations that fire after a message has been delivered for computations on-chain. For doing things off-chain, there's finalization that has to occur so that you know that this is actually needs to be triggered and can't be rolled back. And so even there we have these synchronicity assumptions that we can rely on. We have held back on adding continuations to sends because originally when we were thinking of this, we were designing it for a distributed system, like running in a data center, where it really was asynchronous, but there was no trust between them. So that was the original design for Rolang. When we brought it over here, it continues to work, but there's this extra synchronicity that we're still toying with adding. But the fact that it's split up into a bunch of concurrent processes means that you can do these splits and merges within the execution DAG.
I wondered if you could clarify, I think this will help me understand the last answer too, a little bit about multiple parents versus justifications, and then based on your diagram that's on the screen right now, are all of the parents created equal, or is there like one special primary parent, and where does that live in the block?
Okay, so I would say the main difference is that when you point with a justification, you don't actually include the transactions in the block you've pointed to with the justification. And so with the step parents, you actually include the transactions that are in that block.
Okay, that helps a lot. Thanks. Is there like one primary parent? I know on one of your later slides you had like the thick arrows versus the regular solid arrows, and then I guess it sounds like are step parents sort of analogous to uncles in Ethereum network, or how does that work?
I see. So the main parent is sort of only used because it makes it easier for us to just score. And so we don't rule out the possibility that we could have a more complicated scoring scheme where we also assign weight or add weight to the score if you're a step parent. And so, instead of having like a 0 down there, you could have a 5, or you could make it like sort of weighted by the ordering that you're in. So, you could have like 2.5 or something. And so these schemes are, potentially viable. This just sort of keeps it, at least keeps the scoring as the same with sort of conventional blockchains, or I guess conventional ghosts applied to conventional chains. And so yeah, that's sort of one reason why I've highlighted the main chain, or the main parent in this diagram. Yep. Did you have sorry? Oh yeah, the Amers. So I would say that it's somewhat similar, but the thing about the Ethereum Amer is that I believe you can only include up to 2. I think that's sort of and it's also just an incentive to have less orphaning, so to speak. And so here, I mean, in a sense, it's the same idea, but we're also, because we're all including the transactions that are happening, it's mainly for the throughput difference, if that makes sense.
So those were the parents, the list of parents. What were the justifications? The justifications field?
So the justifications are pointers to the latest blocks that the creator of the block sees, right? And so it kind of, one thing I've sort of left out with these diagrams is the fact that if there's 2 validators, then there should always be at least explicitly 2 justification pointers, 1 for each validator. And so the thing is, though, that sometimes I've not actually included justification pointers because it's implicit in the previous block, or you don't change where you're pointing to from the previous block. And if you have a parent, that's sort of takes the role, or like takes a further role than the justification. So you don't need an explicit justification there too. But essentially, it's important because you want to see what that creator saw as the latest blocks for each of the validators.
Okay, back to the block structure, are the transactions included in there?
Yeah, so when you say transactions, do you mean more like the Ethereum style transaction?
Yes, signed messages from outside the block.
Yeah, okay, so that is part of the new code. So I guess we sort of internally call them deployments. Yeah, that's where they would go.
And then it's pretty common for blocks to include like an arbitrary data field. Do you think you would include that?
I see. So something that adds non-determinism, or maybe like a version field and that kind of thing?
Yeah, sometimes they put the client name, or like if it's a mining pool, they'll put in something. There's just like, I don't know, you get like 32 bytes and you can put in whatever you want.
We haven't really sort of thought what we're going to include for that. I guess because it's not really core to running the simulator, and that's sort of our priority for this block as of now.
If you wanted to do something like that, you could always just send to a ground term in the block, and it will be immediately discarded, but you can see it there in the block. I think we're about 15 minutes over, so we should let Joe have his turn. Thank you.